Hi everyone! In this video, I will demonstrate our recent work on vulnerability scanning for large software repositories without building them. Bob is a developer. He is very busy with developing new modules in his project and spends little time on program testing and analysis. Therefore, the system he develops often contains many bugs, some of which are even security vulnerabilities. To improve the system reliability, Bob and his teammates follow the common practices in industry and conduct security auditing before the release of the product. Typically, there are two manners of security auditing. First, they can hire a group of security experts to check the code and find the underlying bugs manually. However, this plan is very labor intensive and can cost a lot of money to hire such security experts. Second, they can use automatic code auditor, such as symbolic static analyzers. One example is the Facebook infer, so that they can detect the bugs automatically. Unfortunately, existing code auditors are often relied on the successful build of the project and also very hard to extend for diverse bug types. To fill the gap, we propose a novel repo level AI auditor named Repo Audit. Notably, our Repo Audit is the first repo level AI auditor that can support large scale code analysis. We can even support the bug detection upon Linux kernel packages. Basically, the user of the repo audit only needs to specify the prompts to define the bugs and offer some buggy patterns as examples. Then our repo audit can behave as an agent and interact with the repo and scan the repo with language model. So finally, they can give the bug reports. Compared with existing code auditors, repo audit has several significant advantages. First, the user don't need to build the projects anymore. They don't need to solve some tricky problems in the project configurations and compilation. Second, repo audit is very easily to extend to other bug types. So our current version can support top 25 CW bug types, including non-pointer dereference, use-step-free, SQL injection, and so on. Third, repo audit has multilingual support. We can support analysis of programs in the C, C++, Java, Python, and JavaScript. Now I will show a demo of scanning a C and C++ project with repo audit. Here is a program we want to analyze. The name of the subject is SOFA PPRPC, which is a lightweight RPC framework. So in this demo, we only focus on non-pointer dereference as the target bug types as the demo. So in VS Code, we can search the non-value. Here we can find there are 300 non-values in this project, and each of which can potentially introduce non-pointer dereference in this program. So now we will utilize repo audit to track the propagation of this faulty value and to see whether NPD can be introduced in the program. So to run our repo audit, we can just execute this comment. So firstly, we need to specify the bug types, and also we need to specify the projects. And now we can begin the scanning. So in this window, we have several panels. So basically, repo audit just analyze each functions and preserve some information in the agent memory. So right now, he is scanning the function named the pass message and focus on the non-value at line 23. So basically, this non-value will be propagated back to the caller function of pass message. So now the LM just analyzes this function and make a decision. That is, decide which function that the auditor needs to analyze. Okay, now we obtain this message. So it shows that the non-value will be returned as a return value. So this function will be the last one we analyzed. So this is the current function, which is a caller function of pass message. So currently the LM just scans this caller function and focus on the function invocation at line 157. So at this line, the return value can be null. So this means the value of pointer v can be null at this program location. Okay, now LM can be aware of this null value, so reports this bug here. And so in this case, we can preserve this propagation path in the memory and also record the relevant functions here. But now we focus on another invocation site, that is the invocation site at line 165. So here we found that the return value can be null. So the variable JSON can be assigned with null value. So this value will be returned as the return value of this function. So language model will analyze this function and obtain such fact, and then retrieve the caller function, that is pass message again. So in this case, we'll find this function will be invoked at line 32, just this line. So this means the field JSON, this variable, can be null. So based on these facts, we can report the second non-pointer dereference at this point. So we record all these bugs in the memory of the agent, and also we have such statistics to record the input token cost, output token cost, and also the financial cost. So as you can see in this panel, we only cost less than 0.1 US dollar to discover these two bugs. So this shows our approach is very economic. So we will track some other program paths to see how this non-value is propagated. So due to time limitation, we will not show the other details. We also conduct more experiments using repo audit upon open source projects. The bug types we focus include different kinds of memory corruptions, including non-pointer dereference, memory leak, use stuff free, and so on. Within 1 week, we can discover 42 true bugs, and 27 of which have been confirmed by developers. On average, each project, repo, or package only costs 0.58 hours and around $3 on average. And the precision can reach around 65%. So overall, we can outperform the build-based state-of-art analyzers such as Facebook Infer. For more information, please access our organization webpage in the GitHub. We have released the technical report, bug list, and also source code of repo audit. Thank you for your time and attention.